Hello, my name is Jeff Bosser. I've developed a non-mathematical model of the space-time continuum that describes why the speed of light is a constant. Imagine a bowling ball rolling on a conveyor that is moving across a checkered tile floor. If the bowling ball has a constant velocity, then it will travel past all objects in its path at the same speed, meaning that regardless of the speed of the conveyor along the floor, the ball will roll over a seam on the conveyor at the same speed that it will pass over a seam between two tiles. Clearly, this is not the case here. How can light travel past all objects in the universe at the same speed when they all can move at different velocities, like the tile and the conveyor? This is one of two enigmas that I will unravel, and that until now no one has clearly demonstrated. The second enigma has to do with the theory that nothing can ever achieve the speed of light as put forth by Albert Einstein. My model also makes this claim that the speed of light is an unreachable limit, but it shows how and why without math. One thing that has always bothered me about saying that an object can reach speeds close to that of light but cannot reach light speed is this. Say you have two rockets and an observer out in space, and the two rockets take off in opposite directions and reach 60% of the speed of light relative to the observer. How can the velocity between one rocket relative to the other be less than the speed of light? Their combined velocities should add up to be 120% of the speed of light. So, why is the speed of light always the same, and why can't anything achieve light speed? Obviously, these questions are related to the motion of an object through space. So it occurred to me that if I can understand how an object moves through space, then I can understand these enigma. Motion is defined mathematically as distance over time. So, first task is to define both space and time. In order to do that, I have to understand how I perceive each. Space is perceived as the potential extent of locations that can be occupied. Time is perceived as lack of change relative to some other change. The hour hand changes less than the minute hand, and so it requires more time to affect the same amount of change. Motion is then both some lack of change in location and some extent of change in location. In other words, a jump or series of jumps through space with a dwell time between each jump. Of course, these short jumps through space of the trillions of particles that make up an object out of phase with one another cannot be seen directly by the human eye. All that we can perceive is the smooth, continuous motion of the object. However, if we could zoom in on the smallest particle that makes up an object and slow the passage of time, we might see the particle jump through space. And if we mark these jumps, we could create a three-dimensional map of the particle's motion. Think of a 2D map like the one on the right. Like our 3D map on the left, past locations are marked in blue. The path ahead is marked in red, and the current location is where red and blue meet. Also, if we think of each dash marking the path as a footprint, then the farther apart they are spaced, the faster the person walks or runs. For the remainder of this animation, I am using red to indicate locations in space that the particle will occupy, and blue for those that the particle has already vacated. Since the particle is moving from blue to red, it is equivalent to saying that the red locations are moving toward the particle and the blue ones are moving away from the particle. Here the particle is moving from left to right. If we, the observer, change our velocity relative to the particle appears to move slower. Marks are closer together, or faster. marks appear farther apart. If we match the velocity of the particle, it appears to be stationary and has no path. And if we exceed the velocity of the particle, it appears to change direction completely and moves to the left. Hence the red marks on the left and the blue on the right. No force acted on the object, but its velocity appeared to change when ours changed. So what happened? Well, let's ignore the red marks for ease of illustration and assume that the particle is traveling in two opposite directions at once, meaning that the observed velocity of the particle is the difference between the velocities in each direction. The two opposite paths of the particle through space are shown here. If it follows the top path, it will move toward the right, and if it follows the bottom, it will move to the left. And since the spacing between the marked positions of the top path is greater than those of the bottom, the velocity of the particle to the right will be greater than the velocity of the particle to the left. The net effect on the particle can be seen when we overlap the two paths and ignore the red marks. Since the jumps are instantaneous, it may be hard to see the direction of motion, so I will play the last sequence again with the red indicators showing the direction of motion. Remember that, unlike red marks, blue marks travel away from the particle. Their direction of motion is indicated on the bottom. The particle's motion is indicated on the top. Now, instead of two opposite directions, let's map all directions. As you can see, this will cause the marks to form red and blue spheres around the particle. Since the red marks move toward the particle, the red spheres shrink in diameter, while the blue spheres increase in diameter as they move away from the particle. By looking at the cross-section of all the spheres created where a plane intersects the particle, we can map the space that passes through the particle parallel to the plane. And when our velocity changes relative to the particle, the spheres become offset as shown here. When we put the model in motion, the particle moves from left to right. This is the key difference between this model and the theory of relativity. This constant motion model assumes that all particles of matter are traveling through space in all directions at a constant velocity. That velocity is the speed of light. Therefore, the red and blue spheres are decreasing and increasing their radius at the speed of light. Any change in velocity that is witnessed is the result of the spheres of one particle being offset from those of another, causing the particle to move at some small fraction of the speed of light relative to the first particle. In a universe such as ours, with no fixed stationary or stopped reference point, it is impossible to tell which object is motionless and which is moving, or even accelerating if the force of acceleration acts equally on every particle of the object. When we look at a particle's blue relatively offset sphere map and change our velocity relative to the particle, we see all the past spheres become offset from one another. But if the particle is the one changing velocity, we see that only the current and future spheres are affected. So, now to answer our earlier question, why do we see the past and future locations of a particle become offset from one another when only we, the observer, and not the particle, change velocity? The answer is that we, the observer, are also a particle. And if we add the red spheres to our ROS map, we see that as soon as a particle begins to accelerate, the red spheres become offset. Since all space that travels through the particle is defined by the red spheres, and a particle's own spheres always appear centered to itself, all the spheres of other particles observed by the first particle will be offset by the amount that the red spheres of the first particle are offset when viewed from the observed particle. Let me repeat that. All spheres of other particles observed by the first particle will be offset by the amount that the red spheres of the first particle are offset when viewed from observed particles. In this model, light is a distortion on the space that travels through a particle. This means that space, and as a result, the spheres, are traveling at the speed of light. In the next few clips, light is represented as a yellow sine wave emitted from a particle and traveling to our right. The sine wave doesn't necessarily look like a photon of light would actually look like in this model, but we don't care. It represents repetitive change over time and can therefore be grafted onto this model. We see here that as the velocity of the light source changes relative to the observer, the frequency of the light changes. This is the Doppler effect. However, the velocity of the light must remain constant regardless of the velocity of the light source. Let's see what this model reveals about the first of our two enigmas, the constancy of light. In this clip, there is a particle to the right of the light source that is represented as a red dot, and this particle does not move relative to us. I will refer to this red particle as the observer. Since the light source is moving through space at the same velocity as the observer, light from the source passes the observer at the same speed as if it were emitted from the observer. Notice how the outer sphere of both the source and the observer remain aligned. This is to be expected because both the light source and the observer are not moving relative to one another. Now, when the source moves toward the observer, its spheres are offset to the right. But look, the outer sphere of both the source and the observer, whose spheres are not offset, remain aligned. The frequency of the light has increased, and it takes less time for 7 cycles of the waveform to pass the observer, but the light passes the observer at the same velocity as when the source was stationary. Here the source is moving away from the observer, but yet again the light passes at the same velocity as if it had been emitted from the observer. At this point you may be wondering what's going on here. I saw it, but I don't quite understand it yet. Well, let's take another look at all three scenarios at once. On the top, the light source moves away from the observer. In the middle, both the observer and the light source are not in motion. And on the bottom, the light source moves toward the observer. The key to understanding the first enigma of the speed of light is in understanding that although the spheres are offset from one another, their edges always move away from their centers by the same amount. This is the first animation of this phenomenon ever made. This model has shown us how the speed of light can be constant. Now let's see why our two rockets could not exceed the speed of light. In this clip, we see the last 9 spheres of 3 particles, an observer in the middle and 2 on either side moving in opposite directions at 50% the speed of light. If we overlap the sphere map of the observer with the map of the particle on the right and zoom in, we see that at half the speed of light, there are twice as many dark blue sphere edges in the direction of motion than light blue sphere edges at the observer's velocity. And as we change our velocity to match the particle on the left, the spheres of the observer become offset along with the spheres of the particle on the right. Yet they must maintain their offset ratio relative to each other. So when our velocity matches the velocity of the particle on the left, there are still twice as many dark blue sphere edges in the direction of motion than light blue sphere edges. They are just bunched closer together. The conclusion that we draw from this is that as a velocity nears the speed of light appears to increase. Velocity is not linear, and it takes more change in velocity at higher speeds to reach the same amount of change in velocity as at lower speeds. Okay, to review. Here's a composite animation answering both questions at once. The top shows why the speed of light is a constant, and the bottom shows why the speed of light cannot be exceeded. I made this animation because I could not find a non-mathematical explanation for the fact that light is a constant. Math is a wonderful tool, but it adds a layer of abstraction that hides the reality underneath. One becomes concerned with mathematical relationships rather than the physics that these relationships describe. I love animations because they are models that mimic reality but dumb it down and call it out so that it can be held in memory. I hope that this animation will become a framework on which to hang the mathematics of relativity and quantum theory and even chemistry. Thank you for your time.